Hi, in this lesson we're going to deal with atmospheric energy transfer. Now, if you have not already watched the videos before this on the heat budget and on energy balance, then you really should watch those first. So far, what we've established is that the sun's energy arrives at Earth and 51% of it is absorbed by the surface. 49% of it is shed back into space, and eventually all energy is recycled into space. In our second lesson, we understood how, given that that energy has been received by the Earth's surface, we learned to understand why the energy is not evenly distributed over the Earth's surface. And in this lesson, we will take the next logical step and we'll understand how, if given that we know the equator is warmer and the North Pole is colder, why doesn't the North Pole just keep getting colder, and why doesn't the equator just keep getting warmer? So what we need to ask ourselves is, the Earth must have a mechanism for moving energy from the equators to the poles and back again in order to find that equilibrium. And that's why we talk about energy transfer. How does the Earth transfer energy throughout its atmosphere? How does it circulate heat? So, on the screen is basically a kind of summary of what I've just said. And I'll leave you to pause the video and read that for yourself. The place that we need to start is with something called the multiple cell model of atmospheric circulation. Here's what it looks like in simplified form. Now, the first thing to know is that what happens below the equator is basically the mirror image of what happens above the equator. So as far as your understanding of this is concerned, you can just concentrate on what's happening in the northern hemisphere, in the northern half of the world, because everything that happens there happens in reverse in the southern half of the world. The world's atmosphere surrounds us, surrounds the planet, and it is divided into 3 cells: Hadley, Ferrel, and polar. Now, where you need to have some imagination is to understand that you'll see the Hadley cell over here, and you'll see a corresponding Hadley cell over there. And that's because this is a slice, a cross-section through these cells. In actual fact, these are tubes of air that circulate the globe, wrap themselves around the globe, and those tubes of air are essentially spinning. Warm air rises. As it gets cold, it wants to sink, and round and round and round the Hadley cell goes. The same thing with the Ferrel cell, and the same thing with the polar cell. Through these 3 cells, heat is moved from the equator and communicated through the system towards the poles, and cold air is recycled into the system and circulated back towards the equator. And we need to be able to describe and explain that journey. This is a slightly more complex diagram, and it serves us the purpose of familiarizing ourselves with some terms. When we talk about the equator, you might hear me refer to the equatorial low. And that is because, as you can see on the diagram, the air and the Hadley cell is rising away from the equator. And so it is low pressure air. Warm, rising, low pressure air. As the air goes through the Hadley cell, it then cools and sinks, and so it is therefore high pressure air, because cold falling air puts pressure on the Earth's surface, and so we have the subtropical high. From there, the air is transferred into the Ferrel cell. As it does so, it moves over the Earth's surface and gets warm, so it rises again. Warm, rising air exerts less pressure on the Earth's surface, and so this zone is known as the subpolar low. and then the air is transferred through the polar cell, gets cold, and sinks, and cold, sinking air puts pressure on the Earth's surface, and so this is called the polar high. And then this system acts a bit like a conveyor belt, circulating the energy. You'll also hear me refer to surface winds. The Earth's surface winds that kind of we experience as humans, they move in defined patterns, and they have names as well. And you might hear me talk about trade winds. These are the winds that move over the surface of the Earth, and they are the bottom movement of air in the cell that corresponds to that zone. So the Hadley cell air rises up, spreads north, gets cold, sinks and falls, and then returns over the Earth's surface. And that's what these arrows are representing, because remember, the Hadley cell wraps itself all the way around the world between 0 and 30 degrees. And so wherever it's contacting the Earth's surface, it creates these surface winds. Why are they curved and why are they at the angle they're at? We'll get to that. It's also worth revising the degrees of latitude at which these events take place. 0 degrees is the equatorial low, 30 degrees is the subtropical high, 60 degrees is the subpolar low, and 90 degrees is where we would find the polar high. Now, that we've established those basics, we can look at a more complex diagram, and this one attempts to communicate to you in slightly more graphic detail the three-dimensional nature of the Hadley, ferrule, and polar cell. Don't worry that in this diagram that's called the mid-latitude cell. For our purposes, we'll ignore that and we'll refer to it as the ferrule cell. All I want you to take from this diagram is there's the cross-section of the Hadley cell with rising air at the equator, spreading, getting cold, and sinking before returning into the system. You can see that represented by this arrow here, rising where it's warm, spreading, getting cold, and sinking before returning into the system as a surface wind. And you can see how in this graphic that is partially representing the three-dimensional nature of these cells which wrap their way around the world. So let's start off with the Hadley cell, the first cell nearest the equatorial low. The Hadley cell starts at the thermal equator. The thermal equator is the term we use for where the sun is directly overhead at 90 degrees. Without getting into a very long explanation, which this video wouldn't be useful for, 0 degrees, known as the equator, is not necessarily the place that's receiving the most of the sun's energy. Because the angle of the axis of the Earth varies during the year relatively to the sun, the position at which the sun is overhead in the sky can vary to either side of the equator. So all we're really saying here is the zone at which maximum heating is being received from the sun is called the thermal equator. And that is where the sun is overhead, and that causes the air to rise because it is warm. And on this diagram you can see the rising warm air. Now it moves directly up into the sky because it's warm, and this causes a state of calm called the doldrums to take effect at the equatorial low, which is very dangerous to shipping that relies upon sail power. The rising air doesn't just rise off into space, that would be a disaster for all of us. Instead, it's forced to spread. Some of it spreads south into the southern Hadley cell, but we're not going to worry about that. We're going to concentrate on the northern cells. And it spreads north. And as it does so, it cools and it falls because cool things sink. And the cool air sinks as high pressure air at the 30 degrees subtropical high. It's called the subtropical high because it has cool, high pressure air falling upon it. Some of this air is pulled back into the Hadley cell, and round it goes. as a surface wind. That's a wind we experience at the surface of the Earth. Some of the air, however, after it has cooled and fallen at the subtropical high, spreads northwards and feeds the next cell along. Let's look at these surface winds. You'll see that though this is a cross-section, in reality the surface winds, the winds moving over the surface of the Earth, are curved. They're curved due to the spin of the Earth. And a separate lesson on the Coriolis force is available if you want to look at that in some detail. But all you really need to understand right now is that because of the Earth's spin, the winds are curved by that force, and that force is known as the Coriolis force. As I mentioned, some energy feeds the next cell along, known as the ferrule cell. A little extra information. Because of all this very rapid rising warm air here, you get big cloud systems, big cumulonimbus cloud systems, and that explains why we have very, very heavy rainy seasons in the equatorial zone. So what have we covered so far? Well, we've covered that the equatorial low is where the sun is overhead and the most heating occurs. That is, generally speaking, around 0 degrees. As the air is heated, it rises, and it is forced to spread. As it spreads, it cools, and at around 30 degrees, otherwise known as the subtropical high, that cool air begins to sink. Because it is falling, it puts pressure on the Earth, and it's referred to as high pressure air, which is why it's called the subtropical high along this 30-degree line. Some of that air returns into the Hadley cell to complete the Hadley cell cycle. As it does so, it is curved by the spin of the Earth in a process known as the Coriolis force. Some of the air, though, moves this direction to feed the next cell along, known as the ferrule cell. Now I'm going to skip the ferrule cell for a good reason. We're going to jump up to the polar cell now, and you'll see why at the end. The polar cell is a band of cold air that circulates at 60 degrees. It's high pressure because, as you can see here on the diagram, it is falling. It's very cold at the North Pole, and so that air sinks as high pressure air. It has nowhere else to go but to spread out over the Earth's surface. As it spreads out over the Earth's surface, it picks up heat from the Earth, and what does warm air do? Well, warm air rises. Some of it is forced to spread back north to rejoin the polar cell, and some of it spreads south to feed the ferrule cell. So you're seeing here that the ferrule cell is actually really a product of Hadley and polar, and that's why I'm dealing with ferrule last. Now I've mentioned that as the surface winds of the polar cell move over the Earth's surface, they get warmer because of the heat radiated by the Earth, and they begin to rise. The air is still pretty cold, but it is just warm enough to rise. And it's for this reason, by the way, that at this latitude, you'll notice Britain is in this zone, we get such varied mixed weather because of this interaction of the cold and the warm air. And a bit like your breath on a cold window pane, where the warmth of your breath meets the coldness of the window pane, condensation occurs, where this cold and this warm air meet, you get lots of cloud systems condensing and weathers and lots of varied weather. And that's the extra knowledge we could take on board there. But in summary, the polar at 90 degrees, North Pole, the air is very cold. Cold things sink, so we get high pressure air falling. It has to spread over the surface of the Earth. As it does so, it warms up and rises at the polar low. It then rejoins the polar cell to complete that cycle, or some of it spreads into the ferrule cell. So let's deal with the ferrule cell. The ferrule cell is thermally indirect. That means that it is not controlled solely by the sun, but by the cells on either side of it. If you've ever played with Lego and you've had those wee gears that mesh together, you'll know that when one cog turns this way, the next cog along turns in the opposite direction. And very much these cells operate like gears or cogs. So that's a way to remember the direction of the movement. What's happening here is that the spread of the energy from the Hadley cell, where the Hadley cell joins the surface of the Earth, it joins into the ferrule cell, and where the polar cell spreads to feed back into the polar cell, some energy joins into ferrule. And so the ferrule cell is really the interaction of cold air being fed from the polar and warm air being fed from the Hadley. And that creates the ferrule cycle. And so you can say that it transfers heat from Hadley to polar, and from polar to Hadley. So in many ways, even though I've left it to last, the ferrule cell is the most important one, because it really explains how energy gets from the poles to the equator and from the equator to the poles. And that helps us explain why the equator doesn't just continually get warmer and warmer and warmer, and why the poles don't just get continually colder and colder and colder. At 30 degrees, where you see there's falling cold air, that creates high pressure air at the subtropical high. Some teachers will refer to this as the horse latitudes. I choose not to, as this is complex enough already, but I just thought I'd mention the note. Because this air that's falling is high pressure, it can't contain much moisture, because the molecules of air are more densely packed together. Because it's falling, it's getting compressed and squeezed, and that's why it's called high pressure. And that's why at this latitude, all around the world, if you check the world map, you'll find deserts, and that explains the presence of deserts at the subtropical high. If you check in the southern hemisphere, you'll also find deserts at the subtropical high all around the world, and that explains the locations of deserts. At 60 degrees, the interaction of warm and cold air creates variable weather conditions, as I explained earlier. But the main things to take on board with the ferrule cell are that it is thermally indirect. It's not controlled by the sun so much as the cells on either side of it. And secondly, that it transfers heat from the Hadley cell to the polar cell, and from the polar cell to the Hadley cell. Those two facts there are enough for your understanding of the ferrule cell. Right, now if I'd started this lesson just showing you this diagram, you'd probably freak out. But hopefully now you can start to make sense of something as complex as this. There are three cells: Hadley, ferrule, and polar. The Hadley cell has warm rising air spreading, getting cold, sinking, and returning into the Hadley cell as a surface wind. You can see that the Hadley cell is in fact a three-dimensional tube of air that is spinning and wraps its way right around the Earth between 0 degrees and 30 degrees. You can see where the rising warm air rises and spreads and cools and sinks, but also you can see that the surface winds are actually curved. They are deflected, in fact, by the spin of the Earth itself in something known as the Coriolis force. The polar cell is where we have very cold sinking air causing high pressure systems at the North Pole. That air must spread south. As it does so, it is warmed by the Earth's surface, and warm air will rise. Some returns to the polar cell, but some feeds the ferrule cell. And the ferrule cell is the interaction, the thermally indirect interaction between Hadley and polar. And ferrule assists in transferring energy from Hadley to polar and back again. And that's really the whole story. This is the kind of exam question you can expect to see. Sometimes it is assisted with a diagram just because the examiners want to help you out a bit, because it is complex. And you'll be asked to explain how circulation cells in the atmosphere and associated surface winds assist in transfer of energy between areas of surplus and deficit. Before we get to the model answer, which I'm going to show you, let's just pick this question apart a little bit. If you see reference to circulation cells in the question, it's this question that you're answering. Sometimes it's difficult to tell the atmosphere questions apart. Don't forget, if you're asked to talk about surface winds, make sure you do talk about surface winds. And I've provided you one simple thing to say about surface winds, and that's that they're deflected by the Coriolis force. And don't be put off by terms like surplus and deficit. You have seen those terms before. All this means is that how does the circulation cell move energy from areas where there's too much energy at the equator or at the equatorial low, and areas of deficit, areas where there is more long wave and less short wave radiation, such as at the poles. And if you really don't, if you've not got any memory of seeing these terms before, make sure you've actually watched the first 3 videos referring to heat budget and energy balance. Okay, so let's look at an answer. Structure of this answer is important, just to keep it straight in your head. Start off with the Hadley cell. Warm low pressure rises at the equator, it spreads as far as 30 degrees, the subtropical high where it cools and falls. Now, I'm not going to go through all of this in as much detail as I've just been through it because that's pointless. What I do want to focus on is the level of detail that I'm writing in. Notice that I don't just say warm air rises. I mention that it's warm and low pressure and that it rises. It spreads as far as 30 degrees north, the subtropical high. That's really important. Tell me where it spreads as far as. Name that area and then say what happens. Some air is drawn back into the Hadley cell as surface winds. These winds are curved by the Coriolis force. And that accounts for the Hadley cell. So what is actually a really complicated system can be reduced down to 3 key points. And that's at the end of this longer lesson that you've patiently watched through, that's one of the big revision points. This complex question can be reduced down to some fundamental basics. The ferrule cell. Notice this time I'm proceeding in order. I'm going Hadley, ferrule, polar, just because it's easier to remember that way. As the surface winds of the ferrule cell travel, they pick up heat from the earth and they begin to rise at low pressure at 60 degrees. Again, I'm not going to reteach you all this, but notice my use of technical terminology. I'm referring to surface winds. I'm saying that they pick up heat from the earth, that explains their manner of movement, and they begin to rise as warm air? No, as low pressure air. And where do they do that? At 60 degrees, the polar front. The ferrule cell is powered by cells around it, and it is thermally indirect. Tick. If you want to add anything to that, you might mention that the ferrule cell acts to transfer energy from the Hadley to the polar cell and back again, but I'm trying to keep this simple. And the polar cell. The rising low pressure air spreads from 60 degrees to the pole, where it cools, and it falls as high pressure cold air. It then returns energy to the cycle. I like this phrase. It really reinforces that you've understood the question. And the question is about the circulation of energy through the atmosphere. It's not about the circulation of air. It's the circulation of energy and heat. It returns energy to the cycle as the polar cell surface winds, which pick up heat from the earth and rise as low pressure air at 60 degrees, the polar front. Okay. And that is the end of that. Obviously, we'll revise this in class loads. See me if you've got any questions, whatever, about this, but I hope that's acted as a nice summary. There is also another totally exam question focused lesson on the website, which I would urge you to have a look at.